Have you ever wondered how an AI model can learn to balance a pole, self-drive a car, or even master complex games like Monopoly? It might seem like magic, but behind the scenes there's a fascinating process at work, one that mimics natural evolution. This process is made possible by genetic algorithms, a powerful tool in the world of artificial intelligence. And within this field, one of the most innovative and exciting approaches is something called NEAT. And no, not this NEAT. We're talking about NEAT, which stands for NeuroEvolution of Augmenting Topologies. This approach takes the idea of evolution and applies it to neural networks, allowing them to grow and change in ways that traditional methods can't. NEAT was developed by Kenneth O. Stanley back in 2002 during his PhD at the University of Texas at Austin. His groundbreaking work revolutionized how AI models evolve, enabling them not only to improve their performance over time, but also to enhance their structure and complexity. This allows NEAT to tackle increasingly difficult problems, making it a truly powerful tool in the AI toolkit. In today's video, we're going to break down what NEAT is and how it works and explore its various applications and extensions. Whether you're new to AI or just curious about how these systems learn and adapt, we've got you covered. But before we dive in, make sure to drop a like and smash that subscribe button. It really helps the channel grow and ensures you won't miss out on more awesome content like this. To understand the genetic algorithm, let's imagine a colony of ants trying to find food. At first, each ant starts wandering randomly searching for food. Some ants might get lucky and stumble upon a food source quickly, while others might struggle. Over time, the ants that are better at finding food pass on their strategies to the next generation, and the colony as a whole gets better at the task. In nature, species evolve over generations to become better suited to their environment. This evolutionary process involves several key mechanisms: selection, mutation, and crossover. Genetic algorithms take these principles and apply them to solving complex computational problems, where the goal is to find the best solution from a vast search space, just like the ants finding food. Diving deeper into the process, we have population initialization. Imagine you have a group of ants, each with its own way of searching for food. These different strategies represent the initial population. Some ants might zigzag, others might go in a straight line, and some might wander in circles. Secondly, we have the selection process, where after some time, you observe which ants found food the fastest. These successful ants have a higher fitness and are more likely to reproduce, passed on to the next generation of ants, ensuring that the best food finding techniques are preserved. Next up, we have the crossover process, where successful ants pair up and exchange their strategies. One ant might have been great at navigating around obstacles, while the other had a knack for moving in the right direction. When these strategies combine, their offspring ants might inherit a mix of both traits, potentially creating an even better strategy. To avoid all the ants becoming too similar and potentially missing out on even better strategies, some random mutations are introduced. This could be like an ant randomly trying a new path or speed, which might turn out to be an even faster way to find food. Finally, the new generation is created to go out to find food, and the process repeats. Over many generations, the ant colony as a whole evolves, becoming more and more efficient at finding food. But here's where NEAT takes it to the next level. While traditional genetic algorithms assume that the strategies are fixed, NEAT allows these strategies to evolve and become more complex over time. This means that there are no constraints on the potential evolution of these ants, and that they can evolve to be as complex or as simple as needed according to the set constraints of their environment. This dynamic evolution is what makes NEAT so powerful. NEAT stands out from other genetic algorithms because it doesn't just evolve the ant strategies, it also evolves the way the ants themselves are built. Most traditional methods assume a fixed strategy structure, but NEAT starts simple and lets the complexity grow as needed. Imagine our ant colony starts with simple ants that just follow basic paths. Over time, as some ants prove more successful, NEAT allows these ants to develop more advanced features, like the ability to remember where food was found before, or to communicate with other ants about the best paths. This gradual increase in complexity means the ant colony can adapt to more challenging environments to find food more efficiently. As the ant strategies evolve, NEAT keeps track of which features correspond to which strategies across generations. This is like ensuring that when two ants exchange their strategies, they align correctly so the offspring can inherit the best traits without losing any valuable abilities. The factor that sets NEAT apart the most from other models is speciation, which groups similar ants together. This means that ants only compete with those that have similar strategies, allowing for different types of ants to develop and specialize. For example, some ants might become great at finding food in open areas, while others might specialize in dense forests. This diversity helps the colony as a whole become more adaptable and resilient. So there you have it, an in-depth look at NEAT. Whether you're building AI for games, robotics, or any other application, NEAT offers a dynamic and powerful approach to evolving solutions that are both effective and adaptable. If you found this video helpful, don't forget to like, subscribe, and hit that notification bell so you never miss an update.